Right now, in a building in California, there is a small square of metal being kept colder than anywhere in the natural universe, colder than the space between the stars, roughly 270 times colder than the faint warmth left over from the Big Bang. And in October of 2025, that piece of metal was disturbed once, in a single spot. Everything that had been done to it was carefully undone, and a research team listened for what came back. What came back was an echo. The headlines said it was 13,000 times faster than the fastest supercomputers on Earth. That number is not the interesting part. The interesting part is a single word almost nobody repeated. And whether that word means this is the breakthrough quantum computers have been waiting for. By the end of tonight, you will know exactly. Before we begin, if you enjoy taking a question apart this slowly, a quick like or subscribe really helps this channel grow. It's a small thing for you, but it means the world to me. Now, let's begin. On the 22nd of October, 2025, a research team published a paper that claimed, in careful and deliberately narrow language, that a machine had done something no machine had ever done before. The paper appeared in Nature. The accompanying announcement came from Google Quantum AI, written by Hartmut Neven, who founded that group, and Vadim Smeliansky, who directs its pathfinding work. The claim was that a quantum computer had, for the first time in history, run an algorithm whose results surpassed what the world's fastest classical supercomputers could produce, and whose answer could be checked. Almost every headline that followed picked up the same number, 13,000 times faster. It is a good number. It is easy to say, easy to compare, easy to put in a chart. It traveled around the world within a day, and for most people who encountered this story, that number is the entire story they received. I want to tell you at the very beginning that the number is not the interesting part. The interesting part is a single adjective sitting quietly in the middle of the sentence, and if you were reading quickly, you would have skipped straight past it. The word is verifiable. To understand why that word carries the weight of the whole announcement, we are going to have to go a long way around. We will go back to 1876, to a physicist who raised an objection about the direction of time that has never been fully answered. We will stop in 1950, in a laboratory where a young researcher found that a signal which had apparently died could be brought back from nothing. We will look at a quantity that was invented in 1969 for a paper about superconductors, and then, half a century later, turned out to describe what happens to information that falls into a black hole. And we will end up inside a refrigerator in California, at a temperature colder than anywhere in the natural universe, listening for an echo. But first, let me lay out precisely what was claimed. Because in the retelling, these things get compressed into one lump, and they are 4 separate claims of 4 different kinds. The first claim is about speed. Willow, the processor in question, performed a specific calculation that the best classical algorithms available, running on some of the largest supercomputers on Earth, would take roughly 13,000 times longer to complete. That is a measurement compared against an estimate. The second claim is about verification. The result the machine produced can be reproduced. Run the same algorithm on another quantum computer of comparable quality, and you should get the same answer. Compare parts of it against a physical experiment in a laboratory, and you should find agreement. This sounds modest. It is not modest. It is the first time this has been possible. The third claim is about what was calculated. Previous demonstrations of quantum advantage involved problems designed specifically to be hard for classical computers and easy for quantum ones. They were not questions anyone had. This calculation models a physical experiment, which means the number it produces is a number a chemist or a physicist might genuinely want. The fourth claim is a forecast. Google's leadership suggested that real-world applications might arrive within about 5 years. That is a prediction made by a party with an enormous interest in the outcome, in a field where 5 years has been the standard answer for well over a decade. We will come back to it, and we will treat it as what it is. The team's own way of explaining what changed uses sonar, and it is worth borrowing. Imagine you are searching the seafloor for a lost ship. Sonar will give you a blurry shape and tell you there is something down there of roughly the right size. That is real information, and for most of the history of the technology, it was all you got. What Google argued they had achieved was not merely finding the wreck, but reading the nameplate on the hull. The difference between those two things is not speed, it is precision in a final answer, and precision in a final answer is exactly what you need before anyone will act on what a machine tells them. It is also worth noticing where this announcement sits in a sequence, because the company was careful to place it in one. In 2019, the same group demonstrated that a quantum processor could complete a task that would take the fastest classical supercomputer an enormous length of time. That was the quantum supremacy moment, and we will look at what happened to it, because what happened to it is instructive. Then, in late 2024, the Willow chip solved a problem that had been open for close to 30 years: how to make a quantum computer get more reliable rather than less reliable as you make it bigger. And then this. In 2025. 3 steps, 6 years, each one built on the one before it. Alphabet's chief executive personally promoted the result, and photographs of him standing beside the hardware went out with the release. That tells you nothing about whether the physics is sound. It tells you a great deal about how much institutional weight was placed behind it, and it is worth knowing that weight was there when you are trying to judge the temperature of the language. Now, the algorithm. The team named it Quantum Echoes, which is a marketing name, and I mean that neutrally. It is a good one, because it describes the thing accurately. The technical name is an out-of-time order correlator, which describes nothing to anybody who does not already know what it means, and which we are going to unpack properly a little later. What the machine physically does can be stated in 4 steps, and they are strange enough that I want you to hold them in mind for the rest of this. A sequence of operations is run forward across an array of quantum bits on the chip. Then one single quantum bit in that array is deliberately disturbed. A tiny nudge. One thing. Touched once. Then the exact same sequence of operations is run backward, in reverse order, attempting to undo everything that was just done. And then the result is measured. If nothing had been disturbed, the system would come back almost exactly to where it started. Because one thing was disturbed, it does not. What returns instead is a faint disagreement between where the system is and where it should have been, and that disagreement carries information about how the disturbance spread through everything else. That disagreement is the echo, and here is the sentence I want you to keep, because we are going to come back to it at the very end of tonight, and it will mean something larger by then than it means right now. The echo is the measurement. The machine is not calculating an answer in the way you would normally imagine a computer calculating. There is no arithmetic being ground through, no sum being accumulated. The machine is being disturbed, and then reversed, and then listened to. Alongside the main paper, the team released a second piece of work, carried out with the University of California, Berkeley. This one took the same echo technique and pointed it at real molecules. 2 of them, one containing 15 atoms and one containing 28. The goal was to work out the geometry of those molecules, meaning the actual 3-dimensional arrangement of their atoms in space. Chemists have a standard tool for this, called nuclear magnetic resonance, which is the same physics behind the magnetic resonance imaging machine you may have been inside at some point in your life. The quantum computation matched what the conventional instrument said, and then it went further, returning information about distances that the conventional instrument does not readily give you. Google described that as a molecular ruler. They described the wider ambition with a word they seem quite attached to, a quantum scope, an instrument in the same family as the telescope and the microscope, something that makes visible a thing that was always there and that nobody could see. That is a large claim, and I do not want to hand it to you unexamined. Over the next 2 hours, we are going to take it apart carefully, the physics underneath it, the history it belongs to, the reasons it might be exactly as important as it sounds, and the reasons a number of very serious people think the excitement has run ahead of the evidence. And the question in the title is a real question, not a rhetorical one. Is this the breakthrough quantum computers have been waiting for? I have an answer. It is a clear answer, and I think it is the right one. And I am not going to give it to you until the end, because it will not mean anything until you understand what was actually crossed here. You will have it before you sleep. Suppose I hand you a machine and tell you it has just calculated something that would take every supercomputer on Earth 10,000 years to work out. And suppose you ask me, reasonably, how I know the answer is right. Think about what you would have to do to check it. You cannot run the classical calculation, because the entire premise is that the classical calculation is out of reach. You cannot do it by hand. You cannot look it up, because nobody has ever computed it before. The only thing available to you is another machine of the same kind, which puts you exactly back where you started, because now you have two machines making a claim instead of one, and no independent way to test either. This is not a philosophical puzzle invented for a video. It is the central practical problem of the entire field, and it has a history. Go back to 2019, Google's Sycamore processor, running with 53 working quantum bits. It had 54, and one of them had failed, performed a task called random circuit sampling in about 200 seconds. The team estimated that the same task on the best classical supercomputer available would take approximately 10,000 years. That estimate was the headline. Quantum supremacy, they called it, and the phrase went everywhere. Within days, IBM published a response. Their argument was not that the quantum computer had failed to do what it did. Their argument was that the classical comparison was too generous. Using a smarter algorithm and making full use of the enormous disk storage attached to a supercomputer, rather than trying to hold everything in memory, they calculated that the same task could be completed classically in roughly 2.5 days. 10,000 years, or 2.5 days. That is not a small correction. That is a factor of well over 1 million, and it came from nobody touching the quantum computer at all. It came from someone thinking harder about the classical side. There is something worth noticing about how the field responded to that exchange, because it says a lot about the culture. Nobody was accused of fraud. Nobody retracted anything. Both results were correct as stated. What had happened was subtler and more interesting. The claim had been framed as a comparison, and one side of the comparison was not a measurement at all. It was a projection about how well an unknown future algorithm might perform. You cannot measure the best classical algorithm, because the best classical algorithm has not been invented yet. All you can measure is the best one anyone happens to have written down so far. That is a permanently unstable footing for a scientific claim. Imagine a physicist announcing that a new telescope had resolved a detail no other telescope could resolve, where no other telescope meant no telescope anyone has yet thought to build. It would be true, and it would tell you almost nothing, and it would stay true only until someone thought harder. And it kept going. Over the following years, other research groups improved classical simulation methods further, and the gap narrowed again. The quantum result was never shown to be wrong. What was shown, repeatedly, was that the thing it was being measured against was softer than anyone had assumed. One more thing about that number before we leave it. When people say a supercomputer, they usually picture something like a very large desktop machine. The systems used in these comparisons occupy the floor of a purpose-built hall, draw enough electricity to supply a small town, and are cooled by plumbing rather than fans. They represent the absolute ceiling of what classical computation can do at any price. That is the thing being outpaced, and that is why these results get attention at all. It is not that a laptop was beaten, it is that the largest machine humanity knows how to build was, on one narrow task, left behind by a chip the size of a coin. This has become the recurring shape of the field. A quantum advantage is announced. It is genuine, in the sense that the hardware really did what was described. Then classical algorithm researchers spend a year or two thinking about the problem, and the advantage shrinks, or evaporates entirely. Then a new advantage is announced. The pattern has repeated often enough that a certain kind of tiredness has settled over people who follow this closely. Scott Aronson, who is one of the most careful theorists working on the foundations of quantum computing and one of its most publicly rigorous critics, has described efficiently verifiable quantum advantage as one of the largest outstanding challenges in the field. Not because he thinks quantum computers cannot work, because he understands precisely why claims that cannot be checked are a poor foundation to build a science on. Now, here is the technical reason that random circuit sampling could never be verified, and it is worth understanding because it is exactly what the new result changes. When you run a random circuit sampling experiment, what the machine gives you is not a number. It gives you a string of bits, a long sequence of ones and zeros, sampled from a fantastically complicated probability distribution. Run it again, and you get a different string. Run it 1,000,000 times, and you get 1,000,000 different strings. In a system large enough to be interesting, the same string essentially never appears twice. There is no repeated output to compare. The distribution those strings are drawn from does have a signature, and you can do statistics on it, and Google did. But those statistics themselves require classical computation to evaluate, and the whole point was that the classical computation is out of reach. You end up checking the hard part by doing an easier version of the hard part and extrapolating, which is a reasonable thing to do and is not the same as verification. So the machine produced an output that, by its nature, could not be compared with anything. And I want you to sit with how uncomfortable that is for a moment. We had built an instrument, at extraordinary expense, whose outputs were structurally uncheckable. Not difficult to check, uncheckable, in principle, by any route available to us. It is also worth being fair about why the field went down this road in the first place, because it was not carelessness. Random circuit sampling was chosen precisely because it is provably hard for classical computers under reasonable assumptions, and because it stresses the hardware in exactly the way you want if you are trying to show that a machine is maintaining genuine quantum coherence across a large number of components. As a hardware benchmark, it is excellent. It measures the maximum complexity of the quantum state you can hold together before noise wins. The problem was never that it was a bad test. The problem was that it was a test, and nothing more, and it got described as an achievement. And there is a further difficulty hiding underneath, which is that verification is not simply hard here. It is hard in a way that gets worse as the machines get better. With a small quantum computer, you can simulate the whole thing classically and check everything, but a small quantum computer is not useful. The moment the machine becomes powerful enough to be worth having, it becomes powerful enough that you cannot follow what it did. Usefulness and checkability are pulling against each other, and they always will. Any solution has to work with that tension rather than wish it away. An out-of-time order correlator is different in one specific way, and that difference is the whole of the new claim. It does not produce a bit string. It produces an expectation value, a single number, like a temperature, or a current, or a magnetization, or a density. It is the sort of quantity physics has been measuring for 300 years. And numbers can be compared. If your machine says the answer is a certain value, and my machine, built by a different group, says the answer is the same value, that is evidence. If a physical experiment in a laboratory, using entirely different apparatus, produces a consistent result, that is stronger evidence. You can build a chain. That is the entire argument for the word verifiable. Not that anyone has verified everything, that the quantity, for the first time, is the kind of quantity that admits of verification at all. Whether that is enough is a separate question, and we will get to it. There is a serious counter-argument, which is that verifying on a second quantum computer of comparable quality requires a second quantum computer of comparable quality. And those are not exactly abundant. There are only a handful of machines in the world, in the relevant class, and they are not identical, and access to them is not free. But before we can weigh any of that, we need to understand what an out-of-time order correlator actually is. Not the definition, the idea, and the idea starts in the 1870s, with a man who noticed something uncomfortable about the direction of time and would not let it go. In 1876, a physicist named Joseph Loschmidt made an objection to a colleague's work that was so simple and so difficult to answer that it is still taught today as a problem rather than as a solved question. The colleague was Ludwig Boltzmann, and Boltzmann had been building the statistical foundation of thermodynamics, the explanation of why heat flows from hot to cold, why gases fill their containers, why things fall apart rather than assembling themselves. Boltzmann's account was that these things happen because of counting. There are vastly more disordered arrangements of a system's parts than ordered ones, so if the parts are moving about at random, the system will spend essentially all of its time in disordered configurations. Entropy increases because there is more of it to be in. Loschmidt's objection went like this: the laws governing the individual particles are time-symmetric. Write down the equations of motion for a molecule, reverse the direction of time in them, and you get equations that are equally valid. Nothing at the level of the individual particle prefers forward to backward. So imagine you could reach into a box of gas that has spread out from one corner and reverse every single molecule's velocity. Same speed, opposite direction. What would happen? The gas would retrace its history. Every collision would run in reverse. Every molecule would return along the path it came, and after exactly the same interval, the gas would gather itself back into the corner it started from. Entropy would decrease. The second law of thermodynamics would run backward, using nothing but the ordinary laws of motion. Boltzmann's answer, which is correct, is that this is entirely possible and overwhelmingly unlikely. The reversed configuration is one specific arrangement among an unimaginably large number, and you would have to hit it exactly. Any error at all, in any molecule, and the reversal fails. That answer is right, and something about it never stops being slightly unsatisfying, because it converts the most fundamental asymmetry we experience, that the past is fixed and the future is not, into a statement about probability rather than a statement about law. The direction of time, on this account, is not built into the universe. It is a matter of counting. It is worth pausing on how strange Loschmidt's argument is when you take it seriously rather than treating it as a technicality. Everything you have ever experienced is asymmetric in time. Cups break and do not unbreak. Coffee cools and does not spontaneously reheat. You remember yesterday and not tomorrow. And yet, at the level of the individual particles making up the cup and the coffee, and, for that matter you, there is no rule anywhere that says which way is forward. The asymmetry you spend your entire life inside does not exist in the laws. It exists in the numbers. Boltzmann took this argument extremely seriously, and it is difficult not to notice that he spent much of his career defending a position that a great many of his contemporaries did not accept, and that the acceptance largely arrived after his death. Whatever else it is, this is a question that has cost people something. This is now called the Loschmidt echo, and I want you to hold on to the shape of it, because that shape is exactly what a chip in California was doing in 2025. Run the dynamics forward, reverse them. See what comes back. Loschmidt thought of this as an argument. He did not imagine anyone would ever do it. 74 years later, someone did. In 1950, a physicist named Erwin Hahn was working with nuclear magnetic resonance, which at that point was a young technique. The basic setup is this. Certain atomic nuclei behave like tiny magnets. Put them in a strong magnetic field, and they precess. They wobble around the direction of the field, the way a spinning top wobbles around vertical, at a rate determined by the field strength. If you have a sample containing an enormous number of such nuclei, and you get them all wobbling together, in step, the combined signal is measurable. But the signal fades, quickly, and the reason it fades is that no two nuclei sit in exactly the same magnetic environment. Each one is nudged slightly by its neighbors, by imperfections in the magnet, by the local chemistry. So each precesses at a very slightly different rate. Some run fast, some run slow, and within milliseconds they have fanned out into every possible phase, and their contributions cancel. The signal is gone. That looks like decay. It looks like the information has dissipated into the noise, the way heat dissipates into a room. Hahn showed it had not. He applied a carefully timed pulse that flipped every nucleus through 180 degrees, turned the whole ensemble over. And now, having been flipped, the nuclei that had been running ahead were behind, and the ones that had been lagging were in front. They kept precessing at exactly the same rates as before, which meant that after precisely the same interval had elapsed again, they arrived back in step with one another, all at once. The signal came back. Out of nothing, out of what looked like complete disorder, a pulse of coherent signal reappeared. He called it the spin echo. Now, imagine watching that for the first time, in a laboratory in 1950, on an oscilloscope screen. You have watched a signal die. You have watched it flatten into noise. Then, without you doing anything except a single flip in the middle, the dead signal sits up and speaks again. I do not think there is any way to see that and not feel something. There is a detail in Hahn's story that I find very hard to let go of, which is that he was not looking for this. He was 29 years old, working on something else, and the echo appeared as an oddity in data he was trying to understand for other reasons. That pattern repeats across the whole lineage of this idea, with almost suspicious regularity. The quantity at the center of the Google experiment was also written down by people working on an unrelated problem, as we are about to see. Some ideas seem to arrive sideways, in the peripheral vision of people looking elsewhere. The spin echo is one of the most quietly consequential discoveries of the 20th century, and almost nobody outside physics has heard of it. Every magnetic resonance image ever taken is a descendant of it. If you have ever been inside an MRI scanner, lying still in that tube, listening to it knock and hum, you have been inside an echo experiment. Those knocking sounds are the gradient coils switching, and the sequences they are running are echo sequences, direct engineering descendants of what Hahn found. But the deeper thing the spin echo tells you is not about medicine. It is about the difference between two situations that look identical from the outside. In the first situation, information has genuinely left. It has gone out into the environment, into the walls, into the surrounding air, and it is not coming back. In the second, information has spread out within the system, become distributed across so many parts that no single measurement can see it anymore. But it is all still there. From the outside, both look like noise. Both look like the signal has died. It is also worth being precise about what reversing time means in a laboratory, because it does not mean what the phrase suggests. Nobody at any point makes causation run backward. What happens is that a sequence of physical operations is applied whose combined effect is the exact inverse of the sequence that came before. In Hahn's case, a single well-timed flip does it, because the fanning out was a simple matter of some spins running fast and others slow. In the quantum computing case, it takes thousands of operations applied in precise reverse order. Time keeps going forward the whole while. It is the dynamics that get undone, not the clock. This distinction matters because it tells you where the difficulty lives. Reversal is not hard because time is hard. It is hard because the inverse sequence has to be applied with enough accuracy that the errors you introduce while reversing are smaller than the signal you are trying to recover. Every imperfect operation adds noise. If the noise you add while undoing exceeds the echo you are trying to hear, you have learned nothing at all. Hahn's echo is the test that tells them apart. If the disorder is merely spread out, reversal brings it back. If it is genuinely lost, nothing comes back at all. Hold on to that sentence, because we will use it more than once tonight. Information that has spread out is not information that is gone. And once you have that distinction, you can ask a much sharper question than Hahn was asking. He asked whether the signal returns. The obvious next question, and the one that took another few decades to become answerable, is this. Suppose we deliberately disturb one small part of the system before we reverse it. How much of the signal comes back then? And what does the shortfall tell us about how that one small disturbance spread through everything else? That question is the quantum echoes algorithm. That is the whole of it. And answering it requires a quantity that was invented for an entirely different purpose 19 years after Hahn by two physicists thinking about superconductors. Pour a single drop of ink into a glass of water and watch it. At first, there is a thread, a dark filament sinking, curling, holding its shape for a few seconds. Then the thread begins to fray. It splits into finer threads, and those split again, and the boundaries between ink and water dissolve into something soft. After a minute, there is no thread. After 10 minutes, there is no visible structure at all. The water is uniformly, faintly grey. Now, here is the question I want you to actually think about, because everything else tonight depends on it. Where did the ink go? It did not go anywhere. Not a single molecule left the glass. Every particle of ink that entered is still in there, and if you could examine each one, you would find them all present and accounted for. Nothing was destroyed. Nothing escaped. But there is no longer any place you could point to and say, the ink is there. And there is no sip you could take from anywhere in that glass that would tell you which side the drop entered from. The information about where the ink began has not been destroyed. It has been distributed, spread across the relationships between every molecule and every other molecule in a way that no local measurement can recover. There is a way of testing whether you have really absorbed the distinction, and it is this. Suppose you had a perfect record of every molecule in that glass of water. Position, velocity, everything. Could you say where the ink went in? Yes, trivially. The information is right there in the correlations. Now suppose instead that you can only ever measure one small region of the glass at a time, which is the situation any real experimenter is in. Then the answer is no, and it will stay no forever, no matter how many regions you measure one at a time, because the information does not live in any region. It lives in the relationships between them. That is what scrambled means. Not destroyed, not hidden somewhere specific, relocated into the connections, where local instruments are structurally unable to look. Physicists call this scrambling, and it is one of the most important ideas in modern physics. It is also, routinely, confused with a completely different thing. The different thing is decoherence, and the distinction matters enough that I want to be very careful about it. Decoherence is information leaking out of the system into the surrounding environment. A quantum bit gets nudged by a stray magnetic field, or a photon of thermal radiation, or a vibration in the chip, and a piece of its state goes off into the wider world where you can never retrieve it. In the ink analogy, decoherence is the glass being left out overnight and some of the water evaporating. Something has genuinely left. Scrambling is the ink diffusing. Nothing leaves. Everything stays inside the system, but it becomes inaccessible to any measurement that looks at only part of the system. That distinction is the reason the quantum echoes experiment can work at all. If the disturbance to that single quantum bit had decohered, leaked away into the environment, then running the operations backward would recover nothing, because the thing you would need to recover is no longer in the room. It is precisely because scrambled information stays in the system that reversal has anything to grab hold of. So, how do you put a number on scrambling? How fast does the ink spread? How thoroughly? The answer was written down in 1969 by two Soviet physicists, Alexei Larkin and Yuri Ovchinnikov, in a paper about superconductivity. They were not thinking about quantum computers, which did not exist as a concept. They were not thinking about black holes. They needed a mathematical object that would capture how sensitively a quantum system depends on small changes to its initial conditions. A quantum version of the butterfly effect, the idea that a tiny difference at the start compounds into a large difference later. What they constructed compares an operator that has been evolved forward in time with one that has not, arranged in a sequence that does not respect the ordinary chronological order, hence the name it now carries, an out-of-time order correlator. For nearly half a century, that quantity sat quietly in the literature, cited occasionally by people working on superconductors and disordered systems. It was a specialist's tool for a specialist's problem. It is worth saying plainly why any of this needed a new experiment at all, given that the quantity has been written down since 1969. Out-of-time order correlators are, in a real sense, the hardest kind of thing to measure. Almost every quantity physics measures is a simple average over a system at one moment. This one requires you to compare the system against a version of itself that took a different history, which means that in practice, you must actually run the history and then unrun it, with enough fidelity that the comparison survives. Theorists had the definition for decades. Nobody had the hardware. And then, in the 2010s, it was rediscovered by people thinking about black holes, and it became one of the central objects in theoretical physics. The chain of reasoning that got it there is worth walking through slowly, because it is genuinely beautiful, and because it changes what the Google experiment means. In 2007, Patrick Hayden and John Preskill published a paper with the title Black Holes as Mirrors. The question they were asking was what happens to information that falls into a black hole, the famous information paradox, which asks whether the universe permanently destroys the record of what went in. Their answer, under certain assumptions, was startling. If a black hole is old enough, if it has already radiated away about half its mass, then information you throw into it does not vanish for the black hole's remaining lifetime. It comes back out, almost immediately, in the outgoing radiation, but it comes back scrambled beyond any practical reconstruction. Black holes, on this picture, are not shredders. They are mirrors with a very strange coating. Then Yasuhiro Sekino and Leonard Susskind formalized something that had been suspected. They proposed that black holes are fast scramblers, that they mix information as quickly as it is physically possible to mix it, in a time that grows only logarithmically with the number of parts involved. Not merely fast, fastest. And then, in the middle of the 2010s, Juan Maldacena, Stephen Schenker, and Douglas Stanford proved a bound. They showed that there is a universal ceiling on how fast any quantum system can scramble information, and that this ceiling depends only on temperature. The rate is limited by 2 pi times Boltzmann's constant times the temperature, divided by the reduced Planck constant. It applies to a bar magnet. It applies to a cup of tea. It applies to a piece of iron and to the plasma inside a star. It is worth sitting with what that bound means, because universal results of this kind are extremely rare. Physics has very few statements that apply to absolutely everything. The speed of light is one. This is another. There is a maximum rate at which any physical system, of any construction, at any scale, can distribute information through itself, and that rate depends only on how hot the thing is. A warm system scrambles faster than a cold one, and no system anywhere scrambles faster than the ceiling. And then the second half of that result, which is the part that stays with you, of all the objects in the universe, the ones that reach the ceiling exactly are black holes. Not approximately, not nearly, exactly. And black holes sit exactly at the limit. They saturate the bound. Whatever a black hole is, it is the most chaotic thing the laws of physics permit to exist. Now here is the part I want to land properly, because I think it is the most remarkable single fact in this entire story. The quantity in which all of that black hole physics is expressed, the mathematical object used to state the scrambling bound, to describe the mirror behavior, to characterize how the interior of a black hole shares information with itself, is the out-of-time order correlator. The same object Larkin and Ovchinnikov wrote down for superconductors in 1969. And it is the same object a chip in a refrigerator in Santa Barbara was measuring in 2025. This is not an analogy. I am not saying the two things are similar in spirit. It is the same correlator, the same definition, the same mathematics, applied at different scales to different systems. When Willow measures how a disturbance spreads through 105 quantum bits, it is measuring a quantity that theoretical physicists use to describe the interior of a black hole. Which means that whatever else this machine is, it is an instrument that can be pointed at the deepest open questions in physics and made to return a number. And it means something slightly unsettling about what the first genuinely useful task of a quantum computer turned out to be. It was not solving a problem, it was measuring the rate at which nature hides things. Let me describe the object. Willow is a chip. It is roughly the size of a large coin, patterned in metal on a substrate, and it carries 105 quantum bits. Each of those quantum bits is not an atom, not a particle, not anything you would think of as microscopic in the everyday sense. Each one is a small superconducting circuit, a loop of metal with a particular structure built into it that has been engineered to behave like an artificial atom, with two usable energy levels standing in for the 0 and the 1 of ordinary computing. The design has a name that nobody outside the field says out loud, a transmon. It is a contraction of a much longer technical phrase, and it was introduced at Yale in 2007 for a specific reason. Earlier superconducting qubit designs were exquisitely sensitive to stray electrical charge. A single wandering electron somewhere nearby could ruin the state. The transmon design deliberately traded away some of its sensitivity in exchange for robustness against that charge noise. Essentially, every superconducting quantum computer in the world today, from every major company, descends from that one design decision. To function, the chip must be cold. Not cold in the ordinary sense. The operating temperature is approximately 10 millikelvin, 10,000ths of a degree above absolute zero. I want to give you a comparison for that, because the number is meaningless on its own. The background temperature of empty interstellar space, far from any star, is about 2.7 Kelvin. That is the residual warmth of the universe itself, the faint glow left over from the Big Bang, and it is the coldest thing that occurs naturally anywhere. Willow runs roughly 270 times colder than that. There is nowhere in the natural universe as cold as the inside of that refrigerator. Every place in the cosmos where such temperatures exist, a human being built the apparatus. The refrigerator that achieves this is called a dilution refrigerator, and the physics it runs on is worth a moment. It works by exploiting a peculiarity of helium. Below about 870 millikelvin, a mixture of two different isotopes of helium, helium-3 and helium-4, spontaneously separates into two distinct phases, like oil and water, with a boundary between them. Forcing helium-3 atoms across that boundary costs energy, and that energy has to come from somewhere, so it is drawn out of the surroundings as heat. Push the helium across continuously, and you have continuous cooling. There is no colder continuous refrigeration technology in existence. If you have ever seen a photograph of a quantum computer, that gold-colored chandelier of stacked plates and pipes hanging in a frame, you were looking at the refrigerator, not the computer. The computer is the small dark square at the very bottom. It is worth dwelling for a moment on how much apparatus stands between the world and that chip. The refrigerator descends in stages, each one colder than the last, each one a nested shield against the warmth of the room. Signal lines run down through all of it, attenuated at every stage so that the thermal noise of the wiring itself does not reach the bottom and drown everything. Magnetic shielding wraps the lowest stage. The whole assembly is mounted on isolation to keep building vibration out. And even then, cosmic rays passing through the chip cause occasional bursts of correlated errors, a genuine, measured, documented problem, which means that in a real sense, these machines are affected by particles arriving from space. The picture I want you to hold is of an object that is almost absurdly delicate, being kept in a condition that does not occur naturally anywhere, so that it can hold a pattern together for a few thousandths of a second. Now, the operations. A quantum gate on this hardware is a microwave pulse, a burst of electromagnetic radiation of carefully engineered shape, duration, frequency, and phase, delivered down a line into the chip. A single qubit operation takes some tens of nanoseconds. A 2-qubit operation, which entangles a pair, takes a little longer. These pulses are the entire vocabulary of the machine. Everything it does by shining precisely shaped microwaves at pieces of superconducting metal. And here is the number that governs everything, and it is not the number that gets reported, it is gate error. Every operation is slightly wrong. The pulse is a fraction off in amplitude, or the timing is a fraction off, or the qubit has drifted slightly since it was last calibrated. Willow's 2-qubit gate errors sit somewhere in the region of a few tenths of 1%. Stated that way, it sounds close to perfect. Now consider that a single run of the quantum echoes algorithm involves thousands of gate operations in sequence, and then thousands more running backward. If each operation is 99.7% right, and you perform 3,000 of them, the probability that the whole sequence is right is 99.7% multiplied by itself 3,000 times. That is a very small number. Errors do not add, they compound. This is why I want to correct an impression that most coverage of quantum computing leaves behind. The story is not about qubit count. Everyone reports qubit count because it is a single number that goes up, and it makes for a clean chart. But you could hand this team 1,000 qubits of worse quality, and they could not have run this experiment. What made quantum echoes possible was not that Willow is large, it is that Willow is accurate and fast. There is a subtlety here about what the 105 figure actually refers to, and a certain amount of coverage got it wrong. 105 is the number of qubits on the chip. It is not the number used in the beyond classical benchmark. The circuits that carried the speed claim ran on a defined subset, chosen for fidelity. You use the parts of the chip that behave best. This is completely standard practice and is disclosed in the paper. It is only worth mentioning because the difference between 105 qubits did this and the best portion of 105 qubits did this is exactly the kind of gap where public understanding of these results goes wrong. The speed matters for a reason that sounds mundane and is not. The signal being measured is a small statistical effect, buried in noise, and the only way to pull a small statistical effect out of noise is repetition. The uncertainty in a measured average falls as 1 over the square root of the number of repetitions, which means that to halve your error bar, you need 4 times as much data. To reduce it tenfold, you need 100 times as much. Google reported that the project involved on the order of 1 trillion individual measurements. A trillion. The team characterized this as a substantial fraction of all the measurements ever performed on all quantum computers, ever, combined. Let me put a trillion into a shape you can hold. If you performed 1 measurement every second, without stopping, without sleeping, 1 trillion measurements would take you approximately 31,700 years. You would have had to start before the last ice age ended. The reason this was possible in a reasonable amount of wall clock time is that the machine can complete millisecond-scale measurement sequences in under a minute. That throughput is not a footnote, it is a precondition. Without it, the statistics could not be accumulated, the noise could not be beaten down, and the echo would stay buried. There is one more thing about Willow that has to be in this story, because everything else rests on it, and it happened a year before the announcement we are discussing. In December 2024, the same group published a paper in Nature with a title that gives away nothing to a general reader: Quantum Error Correction Below the Surface Code Threshold. What it described was the solution to a problem that had been open for roughly 30 years. The problem is this: quantum error correction works by spreading the information of one reliable, logical quantum bit across many unreliable physical ones, so that errors on individual components can be spotted and repaired. But the machinery doing the spotting and repairing is itself built from unreliable components. So there is a threshold. If your physical parts are better than a certain quality, adding more of them makes the whole thing more reliable. If they are worse than that quality, adding more makes it less reliable. You are introducing errors faster than you can correct them. For 3 decades, the honest answer to whether quantum computers could ever scale was, we have a theorem that says yes, and no experiment that shows it. Willow crossed the threshold. The team encoded a single logical qubit across 101 physical qubits and measured a logical error rate of 0.143% per cycle, with an uncertainty of 0.003%. More importantly, each time they increased the size of the code, the logical error rate dropped by a factor of 2.14. That factor is what the field cares about. A factor above 1 means the machine gets better as it gets bigger. They also reported that the logical qubit outlived the best individual physical qubit on the chip by a factor of 2.4. The field calls that beyond break-even, and it means the error correction was doing more good than harm, which had never been demonstrated on this kind of hardware before. That result is the ground everything else stands on. Without it, the quantum echoes experiment would have been a curiosity. With it, the curiosity has a road in front of it. I want to put you inside the array for a moment, not looking at it, inside it. You are one quantum bit among 105. You are a loop of superconducting metal patterned onto a chip, smaller than a grain of rice, sitting at 10,000ths of a degree above absolute zero. There is no light here, no air, no sound, nothing above you but the descending stages of the refrigerator, each colder than the last. And beyond that, a room in Santa Barbara, with people in it who will never come any closer to you than this. The sequence begins. A microwave pulse arrives, precisely shaped, a few tens of nanoseconds long, and turns you. Another arrives and couples you to your neighbor, and for a moment, the two of you are no longer separately describable. There is only a joint state that includes you both. Then another pulse, and another neighbor, and now 3 of you are entangled, and then a wider ring, and the pattern spreads outward across the array in a choreography of thousands of operations, each one precisely timed, each one passing something along. You can feel the pattern moving through the array, not as heat, not as motion, but as the growing impossibility of describing yourself alone. Whatever you are is now a fact about the whole array, rather than a fact about you. And then something touches one qubit, once. Somewhere in the array, a single extra operation, a deliberate nudge on one component and nothing else. It is nothing. It is the smallest possible thing that can be done here. And then the choreography runs backward. Every pulse in reverse order, every rotation undone, every coupling unwound. It is played note for note in retrograde, thousands of operations peeling the pattern back the way it came, and it should end in silence. If nothing had been touched, everything would return to exactly where it started, and the array would be as it was, and there would be nothing to report. Almost everything does return. What comes back, instead of silence, is a faint disagreement, a residue. The array is not quite where it started, and the amount by which it fails to return carries the shape of that single touch. How far it traveled, how thoroughly it spread, how much of the array it managed to reach before the reversal caught up with it. That disagreement is the echo, and the machine is not calculating anything, it is listening. Now let me tell you why this is hard. The echo is faint, enormously faint. Out-of-time order correlator signals in large quantum systems are small effects sitting underneath layers of noise from imperfect gates, from thermal fluctuations, from measurement error, from the ordinary imperfection of every physical component. The comparison the researchers themselves used is trying to hear a whisper in a stadium during a concert. That is not far off. There are two things that make it possible at all, and they are quite different in character. The first is physical. The forward and reversed evolutions interfere with each other. Quantum amplitudes adding rather than cancelling. This is constructive interference, the same phenomenon that makes bright bands appear on a screen behind a pair of slits, and it is the single most important resource quantum computing has. When the amplitudes add, the echo signal is amplified above what it would otherwise be. The physics does part of the work of pulling the whisper out of the noise. That is not a trick anyone invented. It is a property of the way quantum amplitudes combine, and the experiment is designed around it. There is a third ingredient, less glamorous than either, and the team was open about it. They do not simply run the experiment and take whatever comes out. They apply error mitigation, a family of techniques for characterizing how the noise on a particular chip behaves, and then correcting the final result for it statistically. This is not error correction. Nothing is being repaired mid-flight. It is closer to what an astronomer does when they subtract the known glow of the sky from an image of a faint galaxy. You measure the thing you do not want as carefully as you can, and then you take it away from what you measured. Error mitigation is standard practice, and it is also, honestly, one of the places where a skeptic would look hardest. Every mitigation technique rests on a model of the noise, and models can be wrong in ways that flatter the result. The counterweight in this particular case is that the molecular experiment provided an external check, a place where the mitigated quantum answer could be laid against a measurement made by a completely different instrument. We will get to that. But it is worth knowing that the raw output of the chip is not the number that gets published, and that this is true of essentially every result in the field. The second is statistical, and this is where the trillion comes in. Even amplified, the signal is a small bias in a noisy distribution. The only way to extract a small bias is to sample it an enormous number of times and let the noise average itself away. And because the precision of an average improves only as the square root of the sample count, the numbers get brutal fast. 4 times the data for twice the precision. 100 times the data for 10 times the precision. So they ran it, and ran it, and ran it. On the order of 1 trillion measurements across the project. The team's own characterization was that this represents a substantial fraction of every measurement ever taken on every quantum computer in history, combined. There is something almost absurd about that, and I do not mean it critically. To obtain a handful of numbers describing how a disturbance spreads through 100-odd artificial atoms, a research group performed 1 trillion separate acts of measurement. Each one collapses a quantum state. Each one is a small, irreversible event in which a superposition becomes a definite outcome. 1 trillion of them, in a refrigerator, over months. It is also worth noticing what the perturbation actually is, because the word can mislead. It is not damage, nothing is broken, and nothing is lost. It is a single additional operation applied to one component, the smallest available intervention the machine can make on itself. The entire experiment is a question about consequence. You do one small thing, and then you ask the universe how far the consequences of that one small thing had spread by the time you tried to take it back. That is a question with a very old shape. It is the question behind every account of chaos, every remark about butterflies and hurricanes, every anxiety anyone has ever had about a small decision. What is new is not the question. What is new is that somebody built an apparatus that answers it with a number. And the result of all of that, compared against what the best classical algorithms could achieve on the largest supercomputers available, was a factor of roughly 13,000. There is one more property of this experiment that separates it from what came before, and the team drew attention to it deliberately. Random circuit sampling, the earlier benchmark, was designed to test a single thing: the maximum complexity of quantum state a machine can hold together before noise destroys it. It is a stress test. It asks how much the chip can carry. Quantum Echoes asks for something harder. It models a physical experiment, which means the machine has to carry that complexity and land on an accurate final number. Complexity alone is not enough. The answer has to be right. Those are genuinely different demands on hardware, and the second one is much less forgiving, because a stress test tolerates a great deal of imprecision as long as the state stays complicated, whereas a measurement does not tolerate any. That is the sense in which this was described as a new class of challenge rather than a bigger version of the old one. Now I want to be careful with that number, because I told you at the start it is not the interesting part, and I meant it. It is a real measurement on one side and an estimate on the other. The quantum runtime is a fact. They ran the machine, and it took a certain length of time. The classical runtime is a projection about how long the best method anyone currently knows would take on hardware that exists. Both halves are stated honestly in the paper, but the second half is a moving target by its nature, and history says it moves. Peer reviewers quoted in the coverage said as much directly. The work was described as truly impressive, and in the same breath as sitting in a category where earlier claims have been eroded as classical algorithms improved. That is not a criticism of the experiment. It is an accurate description of the terrain. What nobody disputed, and this is the part worth holding, is that the experiment pushed into a regime too complex for existing supercomputers to simulate, while remaining open to checking by a second quantum device. Whatever happens to the number 13,000 over the next few years, and something probably will happen to it, that structural fact does not move. Which brings us to what the word verifiable is actually doing, and why I have been holding it back for the better part of an hour. Let us step back for a moment and put the pieces we have on the table together, because we have gathered quite a few of them, and they are about to become one thing. We have an objection from 1876, which says that the laws of motion do not care about the direction of time, and that a system could in principle be reversed. We have a discovery from 1950, which says that this reversal is not only possible, but routine, and that it can distinguish between information that has spread out and information that is gone. We have a quantity from 1969, which measures how thoroughly a disturbance spreads through a quantum system, and which turned out half a century later to describe black holes. We have a chip that is accurate enough and fast enough to run that reversal across thousands of operations and hear what comes back. And we have 1 trillion measurements, producing a number. All of that is machinery. Here is what it is for. The output of this experiment is an expectation value. That means a single number, the average value of a physical quantity, of exactly the same species as a temperature, a current, a magnetization, or a density. Physics has been in the business of measuring quantities of that kind for 300 years. We know what to do with them. And the thing about a number is that it can be compared. It is worth being concrete about why an expectation value behaves so differently from a sample. When you draw samples from a distribution, each individual sample is a random event, and in a large enough space, no two samples ever coincide. There is nothing there to hold two experiments against each other, but an expectation value is what the distribution is about. The underlying quantity, the randomness is scattered around. Two experiments sampling the same underlying physics converge on the same expectation value, even though they never produce a single identical sample. That convergence is the whole basis of experimental science. It is what lets two laboratories on opposite sides of the world confirm each other's work without ever seeing the same individual event. So the change here is not that quantum computers became more accurate. It is that somebody found a way to make them produce the kind of output that science already knows how to argue about. If Google's machine says the answer is a particular value, and a machine built by a different group, on different hardware, in a different building, on a different continent, also says the answer is that value, that is evidence of a kind that random circuit sampling could never produce. 2 bit strings from 2 machines tell you nothing, because the strings were never supposed to match. 2 numbers from 2 machines tell you a great deal. This is what the field means by scalable verification, and the reason it is called scalable is worth spelling out. If every quantum computation had to be checked by an external classical calculation, you would have a bottleneck that gets tighter exactly as the machines get more useful, because the more useful the computation, the more impossible the classical check. That is a road with a wall at the end of it. But if quantum machines can check each other's work, and if the results can occasionally be anchored against a physical experiment, then the checking scales along with the computing. There is no wall. That is the argument. And I think it is a good argument, and I want to now tell you what is uncomfortable about it, because something is. What you have, at the end of this, is a chain of trust that never touches the ground. Consider what verification has meant for every scientific instrument humans have ever built. Galileo pointed a telescope at a distant tower and read the inscription on it, then walked to the tower and confirmed what he had read. That is not a small detail of the story. It is how the instrument earned the right to be believed about Jupiter. The microscope revealed structures nobody had seen, and the way those structures earned belief was that you could culture what they showed you and watch a person recover, or not. Every instrument in the history of science has had, somewhere behind it, a chain of confirmation that terminated in unaided human perception. Somebody, at the end of the line, looked at something with their own eyes and said yes. With a large quantum computer, that chain does not terminate. Not because we have not built the right check yet, in principle, forever. The answer to the calculation is not merely unknown to us, it is unreachable by any route except a machine of the same kind. There is no tower to walk to. So what verifiable quantum advantage actually proposes is a structure of confidence in which machines check machines, anchored here and there, where we are lucky enough that it is possible against a physical experiment. And that is a genuinely new relationship between human beings and knowledge. It is not obviously a bad one. Human knowledge has always been distributed and mediated. You have never personally verified the overwhelming majority of what you correctly believe. But this is different in kind rather than degree, because in every previous case, the verification was possible in principle for someone, somewhere, with enough time. Here it is not possible for anyone, ever. We have started building knowledge that no human being will be able to independently confirm, and we have started doing it without anybody stopping to announce that this was happening. And there is a second layer to this that I find harder to shake than the first. Consider what the machine is measuring. An out-of-time order correlator quantifies how quickly information about a local disturbance becomes unrecoverable by any local measurement. It is, quite precisely, a measure of how efficiently a system hides things from anyone looking at only part of it. So the first genuinely useful task performed by a machine whose answers we cannot independently check was to measure the rate at which nature makes things uncheckable. If you wanted to design a coincidence to be more pointed than that, I am not sure you could. I do not think this is a reason for alarm. I think it is a reason for attention, and I think it is why the word verifiable is worth far more of your interest than the number 13,000, because the word is the field's first serious attempt to answer a question that it will not be able to avoid. Now, the honest counterweight, and it is substantial. Verification in principle is not verification in practice. To cross-check a result on a second quantum computer of comparable quality, you need a second quantum computer of comparable quality. How many of those exist? A handful. They are not identical hardware. Some use superconducting circuits, some use trapped ions, some use neutral atoms, and running the same algorithm on genuinely different architectures is not a simple matter of loading a file. Access is limited and expensive. So the verification the announcement describes is, for the moment, a property the result possesses rather than a thing that has been done to it comprehensively. That is not a scandal. It is an accurate description of an early technology. But there is a difference between saying this result has been verified and saying this result is of a type that admits verification, and the second is what is true. There is a further wrinkle in the practical picture that deserves saying out loud. Suppose two machines of different architecture do run the same algorithm and produce the same number. What exactly has been established? Agreement is powerful evidence, but it is not proof, because two machines can in principle share a systematic error, a subtlety in how the algorithm was compiled, an assumption buried in the noise model, both groups borrowed from the same paper, a shared misunderstanding of what the circuit was supposed to represent. Independent confirmation is only as independent as the assumptions underneath it, and in a field this young, a great many assumptions are held in common by everyone in it. This is not a reason to disbelieve anything. It is the ordinary condition of an early science, and it resolves the same way it always has, slowly, as different groups with different habits and different equipment converge on the same answers for different reasons. It just means the confidence has to be built rather than declared, and building takes years. The other thing worth saying is that verification of this kind does not tell you the machine computed the thing you wanted. It tells you the machine computed the thing you asked for. Those come apart more often than anyone likes. A great deal of what makes computational science difficult has nothing to do with hardware at all. It has to do with whether the model you encoded is a faithful representation of the physical situation you cared about. A quantum computer will answer the question you posed with perfect indifference to whether it was the right question. There is one place, though, where the checking has actually been done. One place where the output of this quantum machine was laid alongside a measurement made by a completely different instrument, on a real physical substance, in a laboratory. And it is the most important part of the entire announcement, and it received a small fraction of the attention that the speed figure did. It involved two molecules. Some atomic nuclei have a property called spin, which means, for our purposes tonight, that they behave like extremely small magnets. Hydrogen has it, carbon-13 has it, nitrogen-15 has it. Most of the atoms that make up a living thing either have it or have an isotope that does. Put such a nucleus in a strong magnetic field, and it does not simply line up. It precesses. It wobbles around the field direction at a rate that is precisely proportional to the field strength. For hydrogen, the constant of proportionality is about 42.58 MHz per Tesla, which means that in a field of 1 Tesla, a hydrogen nucleus wobbles around 42 million times a second. Clinical magnetic resonance scanners commonly run somewhere between 1.5 and 3 Tesla. Research spectrometers used by chemists go far higher. Now, the useful part. No nucleus in a real molecule ever experiences the pure external field. Each one sits in a slightly modified local field, shifted by the cloud of electrons around it, and pulled on by every other magnetic nucleus in the neighborhood. Those shifts and those couplings are not noise. They are a code. From the pattern of frequencies that comes out of the sample, a trained chemist can read the arrangement of atoms in the molecule. This is nuclear magnetic resonance spectroscopy, and it is one of the primary tools by which humanity knows the shape of anything. Kurt Wüthrich shared the Nobel Prize in Chemistry in 2002 for developing it into a method that could determine the three-dimensional structure of proteins in solution, without having to crystallize them first, which mattered enormously because a great many proteins do not crystallize, and because a protein in solution is closer to a protein in a living cell than a protein in a crystal is. Paul Lauterbur and Peter Mansfield shared the Nobel Prize in Physiology or Medicine the following year for turning the same physics into imaging. The technique has been giving Nobel Prizes to different fields for 70 years. It is worth knowing how thoroughly this one piece of physics is woven into the world you live in. The definition of the second, the actual international standard, the one every clock on Earth is ultimately calibrated against, is a count of oscillations of a particular transition in a cesium atom, 9,192,631,770 of them per second. Satellite navigation works because those atomic clocks agree with each other to extraordinary precision. Magnetic resonance imaging works because hydrogen nuclei in your tissue precess at a rate that depends on their chemical surroundings. The behavior of small magnetic moments in magnetic fields underwrites both the way you find your way to an unfamiliar address and the way a radiologist finds a tumor, and it has a hard limit. The couplings between nuclear spins through space fall away with distance, and they do so steeply, as 1 over the cube of the separation. Move 2 nuclei twice as far apart, and the coupling between them is 8 times weaker. 3 times as far, 27 times weaker. Push the separation a little further, and the signal disappears beneath the natural width of the spectral lines, and you cannot see it at all. So nuclear magnetic resonance is superb at short range and progressively blind as distances grow. It will tell you with great confidence how 2 atoms 4 bonds apart are arranged. It will tell you almost nothing about how one end of a long, flexible molecule is oriented relative to the other end. There is a way to feel the 1 over cubed problem rather than just note it. Imagine trying to work out the floor plan of a house by standing in it and listening. You can hear the person in the next room clearly. You can just about hear someone 2 rooms away. Beyond that, there is nothing. Not quiet, nothing. And no amount of listening harder will help, because the sound has fallen below the level of the building's own noise. You could map the rooms adjacent to you perfectly and still have no idea whether the house is a bungalow or a mansion, or whether the far corridor bends back toward you. That is the position structural chemistry has been in for 70 years. Exquisite local vision, blindness at range. And a great many of the questions that matter are questions about range. And that is precisely the range that matters most for the molecules people actually care about. A protein's function is often about how two distant parts of the same chain fold toward each other. A drug candidate's behavior often depends on the relative orientation of groups that are nowhere near each other along the backbone. The place where structural biology most wants to see is exactly the place where its best instrument goes dark. The information is not absent from the sample. That is the crucial point, and it connects directly back to the ink in the glass. The long-range structural information is present in the physics. It is encoded in higher-order correlations among the spins, in the relationships between relationships, 3 and 4 and 5 nuclei at a time. It is not somewhere else. It is scrambled into the connections, where conventional analysis cannot untangle it, because untangling it is the exponentially hard problem that no classical method can perform. Information that has spread out is not information that is gone. What the Berkeley collaboration did was take the quantum echoes protocol and use it as a way of getting at those higher-order correlations. The work was carried out with the University of California, Berkeley, which is not an incidental detail, because Berkeley is where a very great deal of the physics in this story was developed. Erwin Hahn spent most of his career there. The Magnetic Resonance Center carries the name of Alexander Pines, whose group spent decades finding ways to make nuclear spins do things nobody thought they could be made to do. The spin echo went to Berkeley and stayed, and 75 years later, the great-grandchild of the spin echo came back to it, running on a quantum computer. It is worth pausing on how unlikely that sentence would have sounded 10 years ago. The out-of-time order correlator was, at the time, a piece of formalism that theoretical physicists used to argue about what happens inside black holes. It appeared in papers about quantum gravity, about the information paradox, about whether space-time is fundamental. It was about as far from applied chemistry as a mathematical object can get. And then somebody noticed that a molecule full of interacting nuclear spins is, mathematically, a chaotic quantum many-body system, the same category of thing the black hole arguments were about. Not similar to one, a member of the same category, which meant the quantity built to describe one could be used to interrogate the other. That kind of transfer happens more often in physics than outsiders expect, and it almost never happens on purpose. Nobody working on black hole scrambling in 2007 was trying to improve spectroscopy. The experiment studied two molecules. One contained 15 atoms, the other contained 28. Two things happened, and they are of different kinds. The first is the control, and it is the more important of the two. The quantum computation reproduced what conventional nuclear magnetic resonance said about those molecules. It matched. If it had not matched, nothing else in this story would be worth discussing, because the whole argument for verifiability rests on the claim that these results can be checked against physical reality, and this was the check. A quantum computer, running an algorithm derived from black hole physics on a chip colder than interstellar space, produced a statement about the shape of a real substance, and a spectrometer in a laboratory agreed with it. That is the moment where the chain of trust touched the ground. It is one point of contact on two small molecules, and the whole edifice of verifiable quantum advantage currently rests on how many more such points can be established. The second thing is the ambition. The quantum computation also returned information about longer separations than conventional analysis readily provides. Not a faster version of the existing measurement, additional reach. Google called it a molecular ruler, and the framing is that it can measure distances the current methods cannot. If that generalizes, it is a new instrument rather than an improved one. And instruments that fail differently from existing instruments are worth more than instruments that are simply better, because the blind spots do not overlap. Now, the honest scale of it. 15 atoms and 28 atoms are very small molecules. A typical small molecule pharmaceutical has somewhere between 20 and 60 non-hydrogen atoms. A monoclonal antibody, the class of drug behind a great many modern cancer and autoimmune treatments, contains roughly 20,000 atoms. The gap between 28 and 20,000 is not a gap you close by waiting. It is the entire remaining problem. The team said as much. This was published as a proof of principle. That phrase is doing exactly the work it appears to be doing, and it should be read the way the authors meant it. But something did happen here that had not happened before. For the first time, a quantum computer was pointed at a real physical substance, asked a question a chemist would ask, and gave an answer that a completely independent instrument confirmed. Which raises the obvious question, and it is the question that decides whether any of this matters outside physics. Why does the shape of a molecule deserve a machine like this? Go and open the cabinet in your bathroom. Not now, you are trying to sleep. But picture it. Every molecule in there exists because somebody made thousands of nearly identical ones that did not work. That is not a figure of speech. It is a description of how pharmaceutical chemistry is done. You have a target, a protein in the body that is doing something you want to stop, or failing to do something you want to start. You need a molecule that will bind to that protein in the right place, tightly enough to matter, and selectively enough that it does not bind to 40 other things and cause harm. So you synthesize a candidate, and you test it, and it does not work, or it works and is toxic, or it works and the body destroys it within minutes. And you learn something, and you make another one, and another, and another. The attrition is enormous. The overwhelming majority of candidate compounds fail, and most of them fail late, after a great deal of money has been spent. The reason the cost of bringing a single approved medicine to market runs into the billions is not that manufacturing is expensive. It is that the search is expensive, and the search is expensive because prediction is unreliable. Before the argument, the thing being predicted deserves a sentence, because people who have not thought about it tend to underestimate how much rides on geometry alone. A molecule is not a formula. Two substances can have precisely the same atoms in precisely the same numbers and behave entirely differently, because the atoms are arranged differently in space. The standard cautionary example is thalidomide, where two mirror image forms of the same compound, identical in every respect except handedness, the way your left hand is identical to your right, had radically different effects, one therapeutic and one catastrophic for developing children. Shape is not a property of a drug. Shape is the drug. The reason is that biology works by fit. An enzyme holds its substrate in a particular geometry so that a reaction that would otherwise take years happens in milliseconds. A receptor responds to a molecule because the molecule's surface matches its own. An antibody recognizes a pathogen by shape. The old lock and key metaphor is wrong in its details. Real binding involves both partners flexing and settling against each other, but it is right about the essential thing. Function follows form, all the way down. Now, why is prediction unreliable? Because the thing you would need to predict is a quantum mechanical problem, and quantum mechanical problems of this kind cannot be computed. Let me show you why. Because the reason is one of the cleanest and most startling arguments in physics. Take a quantum system made of some number of interacting two-level components. Call it n of them. To describe that system completely, you do not need n numbers. You need 2 to the power of n numbers, because you must specify an amplitude for every possible combination of the component states, and the number of combinations doubles with every component you add. 10 components, about 1,000 numbers, manageable. 20, about 1,000,000. 30, about 1,000,000,000. 40, about 1,000,000,000,000, and you are now beyond what any laptop can store. 50, a quadrillion, and you need a supercomputer. 60, a quintillion, and the supercomputer is struggling. 300 components, 2 to the 300th power. That number exceeds the estimated number of atoms in the observable universe. Sit with that. Not the number of stars, not the number of galaxies. The number of atoms in everything we can see, out to the edge of what light has had time to reach us from. To write down the complete description of 300 interacting quantum components, you would need more numbers than there are atoms available to write them on. This is not a statement about computers being slow. It is not a problem that faster processors solve, or that better programmers solve, or that patience solves. It is a statement about the size of the description itself. The universe apparently has no difficulty keeping track of it. We cannot. There is something worth noticing in that argument that goes beyond chemistry. The universe is running a calculation, continuously, everywhere, that we cannot follow. Every molecule in your body is at this moment doing something whose complete description would exceed our capacity to write down. Not because anything mysterious is happening, because the bookkeeping of quantum mechanics grows faster than any bookkeeping we can perform. We are, in a quite literal sense, living inside a computation we cannot audit. And the proposal on the table is to build a small piece of the same kind of thing and ask it questions. Richard Feynman made exactly this observation in 1982, in a lecture that essentially founded the field of quantum computing. His argument was disarmingly simple. If nature is quantum mechanical, and simulating quantum mechanics on a classical machine is intractable, then stop trying to simulate it classically. Build a simulator that is itself quantum mechanical, and let it do naturally what you were struggling to compute. That is the origin of the entire enterprise, not code breaking, not search. Feynman's proposal was to build a machine that could model nature, because nature is not classical, and if you want to simulate nature, you had better make it quantum mechanical. And that is why the molecular experiment is more significant than the speed record, even though the speed record got the headlines. Quantum echoes is, arguably, the first result in which a quantum computer did the thing Feynman actually proposed it for. It modeled a physical system whose behavior is genuinely quantum, and it returned a number a chemist could take to a spectrometer and check. Now let me be concrete about what would follow if this line of work matured, and equally concrete about how far away that is. Consider a drug binding to its target. The interaction is a matter of shape and charge distribution. Which parts of the molecule present which electrical character to which parts of the protein, and whether the geometry allows them to come close enough. If you could compute that reliably, you would not need to synthesize thousands of candidates. You would compute the candidates, rank them, and synthesize the handful that the computation said should work. The failures would happen in a simulation instead of in a laboratory, and then in a clinical trial. There is a version of this that is personal rather than industrial, and it is the version I keep coming back to. Every disease that currently has no treatment for one of two reasons. Either nobody has looked, or somebody has looked and the search space defeated them. For the rare conditions, the ones affecting a few thousand people worldwide, where the economics of a decade-long empirical search were never going to work, it is almost always the second. There is very probably a molecule that would help. Nobody has the resources to find it by making thousands of things and testing them. That is what the phrase computational drug design is really about. Not speed for its own sake. The possibility that the search stops being a search. Consider a battery. The performance of a battery is governed by how ions move through an electrolyte and how they insert themselves into an electrode material. And those are quantum mechanical processes involving strongly interacting electrons. Battery development today is substantially empirical. You try compositions and measure what happens. Consider a catalyst. The single most cited example in this field is the iron-molybdenum cofactor of nitrogenase, the enzyme by which certain bacteria pull nitrogen out of the air at ordinary temperature and pressure and turn it into a form living things can use. Industry does the same chemistry through the Haber-Bosch process, which requires high temperature and high pressure and consumes on the order of 1 to 2% of the world's total energy production. A bacterium in a root nodule does it in the dirt, at ambient conditions, and we do not fully understand how. The reason we do not is that the electrons in that cluster of iron and molybdenum atoms are correlated in ways that defeat every standard approximation method. It is a textbook example of a problem sitting just beyond classical reach. And consider one more, which has a pleasing circularity to it. Quantum computers are built from materials, superconducting films, junctions, substrates, whose behavior is itself a hard quantum many-body problem. A quantum computer good enough to help design better qubit materials would be a machine that shortens its own development. Now the caveat, and it needs to be as clear as the promise. None of these are things that quantum echoes did. The experiment determined the geometry of molecules with 15 and 28 atoms. Nitrogenase's active cluster is a harder problem than either. A protein is 3 orders of magnitude larger. The resource requirements for the useful cases are, on current estimates, well beyond what any existing machine can supply, and the growth is not gentle. What changed in October 2025 is not that these problems became solvable, it is that the category stopped being purely theoretical. Somebody did a small one and checked the answer. That is a real thing to have happened. It is also, precisely, a small one. It is January 1610 in Padua. A man in a cold upper room has a tube in his hands, about as long as his arm, with a ground lens at each end. He has made it himself, having heard a rumour of such a device from the Netherlands, and worked out the principle without ever seeing one. He points it out of the window at a bright point in the evening sky. He sees the point resolve into a disk, and beside the disk, arranged in a neat line, 3 smaller points of light. He writes them down. He does not know what they are. 3 little stars, he notes, close to Jupiter, and unusually well aligned. The following night he looks again. They have moved, and there are 4 of them. He looks the night after, and the night after that, and over the course of a week, the 4 points shuffle their positions, sometimes vanishing behind the disk, sometimes reappearing on the other side. And slowly, over those nights, Galileo Galilei works out what he is looking at. He is not seeing stars, he is seeing 4 bodies going around Jupiter, which means that not everything in the heavens goes around the Earth, which means the picture of the cosmos that Europe had held for 14 centuries has a hole in it. Now, hold that scene and notice what it was not. It was not a night on which the telescope became useful. On that night, the telescope was a tube with 2 pieces of glass in it, made by an instrument maker with better craftsmanship than most, capable of showing 4 dots. What made it matter was the following week, and the following year, and the following century. Astronomical spectroscopy, the technique that lets you point a telescope at a star and determine what it is made of, did not arrive for another 250 years, because nobody in 1610 had a question of that shape. They did not know that light carried a chemical signature. There was nothing to look for. It is worth being honest about how poor that first instrument was. Galileo's best telescopes, magnified perhaps 20 or 30 times, with a field of view so narrow that finding an object at all was a considerable skill, and with optical distortions that turned every bright point into a small coloured smear. Astronomers who looked through it and saw nothing were not being stubborn. They were being shown a genuinely bad image by a genuinely bad device, and being asked to reorganize their cosmology around it. The instrument was not convincing. It was right. The microscope has the same shape of story. Compound microscopes existed by the late 1500s. Robert Hooke published his drawings of what he saw through one in 1665. Antony van Leeuwenhoek described what he called animalcules, living things in a drop of water, shortly afterwards. And then almost nothing happened with it, medically, for 200 years. The instrument was showing people bacteria. Nobody knew that bacteria caused disease. It took until the 1860s and 1870s, with Pasteur and Koch, before germ theory gave the microscope something to look for. 2 centuries of an instrument that could see the cause of most human death pointed at it, by people who did not know what they were seeing. There is a third example that fits this pattern so precisely that it is almost unfair to bring it up. In 1946, at Stanford and at Harvard, 2 groups independently discovered nuclear magnetic resonance in bulk matter. It was a physics result about the behavior of nuclei in magnetic fields, of interest to a small number of specialists. Chemists began using it to identify compounds in the 1950s. Structural determination of proteins arrived in the 1980s. Medical imaging, the application that made it a household technology, that put a scanner in most large hospitals on Earth, came in the 1970s and 80s, more than 3 decades after the physics. Nobody in 1946 was forecasting hospitals. The physics was the physics. The uses came later, from other people, for other reasons. And here is the part I find genuinely strange. That instrument, nuclear magnetic resonance, is the one the Google experiment is now trying to extend. The story loops. A technique that took 30 years to find its purpose is being handed a new capability by a machine that is currently, by every reasonable measure, about where nuclear magnetic resonance was in 1948. An instrument's first night is never its best night, and the person holding it is almost never the one who finds out what it was for. This is the frame I want to put around the quantum scope claim, because I think it is both more generous and more skeptical than the way this result usually gets discussed. More generous, because the standard skeptical response to a proof of principle on a 15-atom molecule is to say, that is not useful, come back when it does something. And by the standards of instruments, that response is badly calibrated. Galileo's 4 dots were not useful either. Van Leeuwenhoek's animalcules were not useful for 200 years. Judging an instrument by what it can do in its first year is judging it by the least informative moment in its entire history. More skeptical, because the same argument cuts hard against the 5-year forecast. If the pattern of instruments is that they take decades to find their purpose, then a confident timeline attached to the first demonstration is precisely the kind of statement that history does not support. It is not that 5 years is too optimistic. It is that the shape of the prediction, a specific number of years to real-world application, stated at the moment of the first result, has essentially no precedent in the history of scientific instruments. There is a third thing the instrument frame does, and I think it is the most useful of the 3. It dissolves the question in the title. Because, is this the breakthrough, assumes that breakthroughs are events. It assumes there is a day, and before that day the thing did not work, and after it the thing did. And that model is wrong about almost every technology that has ever mattered. There was no day on which the telescope started working. There was no day on which the microscope became medicine. There was no moment at which electricity became useful. There was a long, unglamorous period in which it stopped being a curiosity and became reliable, followed by a period in which people found out what it was for, followed, much later, by the retrospective story in which somebody had a breakthrough. Instruments do not have breakthrough moments. They have a long approach, and then a long wait, and then a use that nobody predicted. There is one more feature of instrument histories that fits this case uncomfortably well, and it is worth stating because it is the least comfortable part. The people who build a new instrument are almost never the people who find out what it is for. Galileo did not discover the composition of stars. Van Leeuwenhoek did not discover germ theory. He died a century and a half before it. Hooke drew cells and had no notion that everything alive is made of them. In each case, the builder handed over a capability, and somebody else, much later, with a completely different question in their head, worked out what it was good for. Which means the honest position on quantum computing right now is that the people making the confident predictions about applications are, structurally, the people least likely to be right about them. Not because they are dishonest, because that is not how this has ever worked. What they do have, and this is the thing worth watching for, is a moment when they become trustworthy. Not powerful, trustworthy. The point at which the readings can be relied upon, cross-checked, and built on by people who did not make the device. Galileo's telescope crossed that line when he pointed it at a distant building, read the inscription, and then walked to the building to confirm what he had read. That is a small and unglamorous act, and it is the reason anyone believed him about Jupiter. He had shown that the instrument told the truth about something checkable, so its report about something uncheckable could be taken seriously. That is exactly, precisely, what the two molecules were. 15 atoms and 28 atoms are the inscription on the tower. They are the checkable thing. The quantum machine said something about a real substance, and an entirely different instrument agreed. It is one small confirmation, on two small molecules, and it is doing the same structural work in this story that a wall of text on a Paduan building did in 1610. Which does not make it a breakthrough. It makes it something narrower and, I think, more interesting. It makes it the beginning of a machine earning the right to be believed. Something happened across this entire field in a very short window, and it is worth stepping back from Google for a moment to see it, because quantum echoes is not an isolated event. It is one data point in a transition that essentially every major group crossed at almost the same time. Between late 2024 and the middle of 2026, every serious quantum hardware program in the world announced a logical qubit milestone. Taken one at a time, each is incremental and technical and would not hold anyone's attention. Taken together, they mark the point at which quantum error correction stopped being a research demonstration and started being engineering. Before the list, one piece of vocabulary, because everything in it turns on the distinction. A physical qubit is a piece of hardware, a superconducting loop, a trapped ion, an atom held in a beam of light. It is fragile, it is noisy, and it holds its state for a short time. A logical qubit is not a piece of hardware. It is a pattern spread across many physical qubits, arranged so that errors on the individual pieces can be detected and repaired without ever looking directly at the encoded information, which would destroy it. A logical qubit is what you actually want to compute with. Every headline figure about qubit counts refers to physical qubits, and the ratio between the two is where the real engineering lives. The reason the last 2 years matter is that until recently, nobody had a logical qubit that outperformed the physical qubits it was made of. Building one that did was the 30-year problem. Let me walk you through them, because the shape of the collection tells you more than any single item. Google's contribution you already know, the December 2024 below threshold result on Willow, the distance, 7 code, the error suppression factor of 2.14. By early 2026, that program had progressed to a 7x7 code, with each increasing code size suppressing the logical error rate by roughly the factor the theory predicts. In March of 2026, the same group added a second kind of hardware entirely, neutral atoms, held and manipulated by light rather than patterned in superconducting metal, as a parallel track alongside the superconducting work. IBM announced 2 processors together in November 2025. The first, Nighthawk, carries 120 qubits in a square lattice and is built to run circuits with 5,000 gate operations. The second, Loon, is stranger and more interesting. It is not built for performance at all, but to demonstrate a kind of connectivity. Loon includes couplers that link qubits, which are not neighbors, reaching across the chip, because a promising family of error-correcting codes requires exactly that, and superconducting chips do not naturally provide it. IBM's stated destination is a machine called Starling, roughly 200 logical qubits, assembled from on the order of 10,000 physical ones, capable of running 100 million gate operations, built by 2028, and available the following year from a data center in Poughkeepsie, New York. That last detail is worth pausing on. There is a street address. A fault-tolerant quantum computer has a projected postcode. Quantinuum, which uses trapped ions rather than superconducting circuits, announced a system called Helios, carrying 48 fully error-corrected logical qubits at an encoding ratio of roughly 2 physical qubits per logical one. To understand why that number caused a stir, you need to know that the surface code, the scheme Google uses, typically requires hundreds or thousands of physical qubits for each logical one. 2 to 1 was considered out of reach a few years ago. It is possible because trapped ions can be moved and connected in ways that a fixed lattice of superconducting circuits cannot, which allows a different family of codes. In March 2026, Microsoft and Quantinuum together reported 12 logical qubits, operating at a logical error rate of roughly 2 in 1,000, below the error rate of the underlying physical qubits, which is the whole point of the exercise. IonQ reported its tempo system reaching 64 algorithmic qubits in the first quarter of the same year, on trapped ion hardware with connectivity between every pair. The variety in that list is itself informative. Superconducting circuits, trapped ions, neutral atoms, 3 physically distinct ways of building a qubit, with entirely different failure modes, different speeds, different connectivity, and different manufacturing challenges. Superconducting chips are fast and can be fabricated with semiconductor techniques, but the qubits sit in a fixed lattice and can only talk to their neighbors. Trapped ions are slower by orders of magnitude, but can be shuffled around and connected to anything, and every ion of a given species is identical because nature made them, rather than approximately identical because a fabrication line made them. Neutral atoms sit somewhere between. Nobody knows which of these wins. It is entirely possible that none of them does, and that the eventual machine uses something not currently on the list. What the diversity buys the field is that a fundamental obstacle in one approach does not stop the others, and, more importantly for our purposes tonight, that a result confirmed on 2 different architectures means considerably more than a result confirmed twice on the same one. And then there is Microsoft's other program, which is the most ambitious and the most contested thing in the field. In February 2025, Microsoft announced Mariana 1, presenting it as the world's first quantum processor built on topological qubits. 8 of them, on a material stack of indium arsenide and aluminium, developed with a team led by physicists at the University of California, Santa Barbara. The idea behind topological qubits is genuinely beautiful. Rather than storing quantum information in the state of a single component, where any stray disturbance can corrupt it, you store it in a global property of the system, a property that is a matter of the arrangement as a whole, and therefore cannot be destroyed by a local disturbance. It is the difference between writing a message on a piece of paper and tying it into the paper as a knot. Smudges do not untie knots. If it works, error correction becomes vastly cheaper because the hardware protects itself. At its build conference in 2026, Microsoft announced Majorana 2. They had replaced the aluminium superconductor with one based on lead, having concluded that aluminium was a dominant source of decoherence in the first chip, and they reported coherence times rising from milliseconds to around 20 seconds, roughly a 1,000-fold improvement. On the strength of it, they moved their target for fault-tolerant quantum computing forward from 2033 to 2029, and a substantial number of physicists do not believe them. I want to present this carefully because it is a live scientific dispute and not my place to settle it. The objection, made most prominently by Henry Legg, is that nothing in the presented data establishes the existence of a topological qubit at all. The technical form of the argument concerns measurement. Demonstrating that you have a qubit requires two independent classes of measurement, conventionally labeled X and Z, corresponding to two different ways of interrogating the state. Critics point out that the published work presents Z measurements without the corresponding X measurements, which means the thing that would distinguish a genuine topological qubit from a more mundane explanation has not been shown. This matters more than an ordinary technical disagreement, because topological quantum computing has a difficult history. The field has seen multiple high-profile papers retracted, including work claiming evidence for exactly the kind of exotic states these qubits require. That history makes people cautious in a way they would not be about a less contested claim. Microsoft's position is that the evidence supports what they have said. The critics' position is that it does not. Both are being argued, in the literature, in public, by people who are entirely qualified. That is what a live question looks like, and I am not going to pretend it is resolved. And it connects directly back to the argument we were making about verification, in a way that is not comfortable. The entire case for verifiable quantum advantage rests on machines being able to check each other. That requires a population of comparable machines, run by different groups, using different approaches, capable of executing the same algorithm and being held against one another. Look at the list again, with that in mind. It is a very short list, the entries are not interchangeable, and several of them are still arguing about whether the others have what they claim. The infrastructure of verification is being built at the same time as the thing it is supposed to verify, which is normal. Historically, every field goes through this, but it means that for the next several years, the phrase verifiable quantum advantage will describe a property of the result rather than an operation that has been performed on it. But step back from the individual disputes and look at the shape of the whole thing, because the shape is remarkable. There is a technological revolution taking place, and it is taking place entirely inside refrigerators and vacuum chambers, in a few dozen buildings scattered across the world. Nothing about it is visible. There is nothing to watch. The machines make no sound that anyone hears, produce no light that anyone sees, and are separated from the room by so many layers of shielding that the room itself is a source of contamination. The people doing it disagree with each other, in print, about whether some of it is real. And billions of dollars of public and private money are moving on the strength of it. That is a very strange thing to be happening in the same world you are lying down in. I want to give the skeptical case its full weight now, at proper strength, because a great deal of what passes for balance in coverage of this field is a sentence of caution attached to the end of a press release, and that is not the same thing. The most serious scientific skepticism about quantum computing does not come from people who think the physics is wrong. It comes from people who think the engineering assumption underneath the whole enterprise is wrong. Gil Kalai, a mathematician who has argued this position for well over a decade, contends that the noise affecting quantum computers is fundamentally correlated in ways that error correction cannot handle. The threshold theorem, the result that says error correction works if your components are good enough, makes assumptions about how errors behave. It assumes that errors on different components are largely independent, or at least that their correlations are limited in particular ways. Kalai's argument is that in a real physical device, at the scales required, that assumption fails, and that noise conspires in ways that defeat the correction machinery no matter how good the individual parts become. Mikhail Diakonov's objection is different and blunter. He points out that describing the state of a quantum computer with a useful number of qubits requires specifying an astronomically large number of continuous parameters, not discrete ones, continuous ones, each of which must be controlled to some precision. His question is simply how anyone imagines controlling that many continuous quantities simultaneously, and he does not think there is a good answer. Neither of these positions is mainstream. Both have been argued against at length by people who work in the field, and neither has been refuted to the satisfaction of the person making it, which is worth noticing, because in physics, that is a meaningful state of affairs. Then there is the more moderate skepticism, which is not about whether quantum computers can work in principle, but about the reliability of claims made along the way. Scott Aronson's position is the clearest example. He is not a doubter of quantum computing. He has spent his career on its theory, but he has been consistently sharp about the gap between what is demonstrated and what is announced, and his identification of efficiently verifiable quantum advantage as one of the field's central open problems is precisely a diagnosis of that gap. There is also a category of claim about quantum computing that is not skepticism at all, but overreach, and since it circulates widely, it is worth correcting on the way past. The most common one is the description you will have heard 100 times, that a quantum computer tries every possible answer at once and picks the best. That is wrong, and it is wrong in an instructive way. A quantum computer does not evaluate all possibilities in parallel and select the winner. What it does is arrange the amplitudes so that the paths leading to wrong answers cancel each other out, and the paths leading to the right answer reinforce. Interference is the resource, not parallelism. Almost every exaggerated claim about quantum computing can be traced back to that single misunderstanding, because if the machine really did try everything at once, it would solve almost any problem instantly, and it does not, and it will not. A second one attaches to interpretation. David Deutsch has argued for decades that quantum computation constitutes evidence for the many worlds picture, that a machine factoring a large number is performing the work across many branches of reality. It is a serious position held by serious people, and it is an interpretation, not a result. The mathematics is interpretation neutral. It works identically whichever picture you prefer, and no experiment distinguishes them. Google claimed nothing of the sort, and coverage suggesting otherwise is not describing the paper. And the erosion pattern is not hypothetical. It has happened. 200 seconds against 10,000 years became 200 seconds against 2.5 days, and then it narrowed further. Anybody assessing a new advantage claim who does not weight that history is not assessing it seriously. There is a related matter that comes up whenever quantum computers are discussed, and it deserves clearing up because the public version of it is wrong in both directions. In 1994, Peter Shaw published an algorithm that would allow a sufficiently large quantum computer to factor enormous numbers efficiently. That matters because the security of a great deal of internet traffic rests on factoring being hard. If you could factor quickly, you could break the public key cryptography protecting banking, messaging, and government communication. The wrong version of this, which circulates constantly, is that encryption is already broken. It is not. Shaw's algorithm requires a large, error-corrected quantum computer, and no such machine exists. The most recent careful resource estimate by Craig Gidney in 2025 brought the projected requirement for breaking 2048-bit encryption down to fewer than 1 million noisy qubits running for under a week. That was a substantial reduction on his own earlier estimate, roughly 20-fold. It is also still 1 million qubits, against a state-of-the-art in the low hundreds. But there is a real version of the concern, and it is genuinely uncomfortable. Encrypted data intercepted today can be stored today, sitting on a disk somewhere, waiting. If a capable machine arrives in 15 years, Everything harvested now becomes readable then. The field calls this harvest now, decrypt later, and it is the reason the United States National Institute of Standards and Technology finalized its first post-quantum cryptography standards in August 2024, years before the machines that would threaten the old ones exist. Nobody waits for the threat to arrive when the damage is retroactive. So that is the skeptical ledger, and it is substantial. Now let me tell you what is not in dispute, because it is easy to come out of a passage like that, thinking the whole field is contested, and it is not. Nobody disputes that Willow crossed the error correction threshold. Nobody disputes that the logical error rate falls as the code grows. Nobody disputes that the quantum echoes experiment ran, that the measurements were taken, that the algorithm did what was described. Nobody disputes that the quantum computation of those two molecular structures agreed with conventional spectroscopy. What is disputed is how far it generalizes, how long it takes, and what the classical comparison will look like in 3 years. It is also worth being fair to the forecasters, because there is a reason they say 5 years, and it is not purely promotional. The remaining work on quantum echoes really is closer to engineering than to fundamental research. The algorithm exists. It has been demonstrated. It has been checked against a physical experiment. What is left is scaling it up and refining it for particular applications, and that is a known kind of hard rather than an unknown kind. Compare that to where the field stood in 2019, when the state-of-the-art was a benchmark with no application at all, and the rate of change over 6 years is genuinely steep. The counter is that just engineering has swallowed decades before, in fusion, in artificial intelligence, in every field that ever had a clear path and found that the path was longer than it looked from the start of it. Both of those observations are true at once, and holding both is more accurate than picking one. Which brings me to the thing that I think is worth taking away from this part more than any specific technical point. There is a natural assumption people make about frontier science, which is that somewhere behind the press releases there is a room of people who actually know, who have seen the real data, who have done the sums, and who are simply choosing how much to tell the public. That room does not exist. The physicists closest to this hardware are in open, published, sometimes quite sharp disagreement about whether one of the leading approaches has produced a single working qubit. The most rigorous theorists in the field say the verification problem is among the largest open challenges in computing. The people making 5-year forecasts are the people with the most at stake in those forecasts, and they know it. This is not a failure of science. This is what the front edge of science actually looks like from inside. Provisional, contested, argued in public by people who respect each other and disagree anyway. It is only from the outside that it ever looks like a settled body of knowledge with a spokesperson. Almost nobody outside a research field ever gets to see that view, and I think seeing it clearly is worth more than knowing any particular fact about quantum computing, because it is the correct way to hold every claim of this kind you will encounter for the rest of your life. I told you at the beginning that the question in the title is a real one, and that I had an answer, and that I would give it to you before you slept. So here it is, plainly, without hedging. Is this the breakthrough quantum computers have been waiting for? No, not in the way the word breakthrough invites you to imagine. And yes, considerably more than the skeptics allow. And the reason those two things do not contradict each other is that we have been asking the question in a shape that does not fit what actually happened. Let me take the no first, because it is the part people usually want. Nothing became possible in October 2025 that was not possible in September. No disease became curable. No material became designable. No encryption became breakable. The molecules involved had 15 and 28 atoms, which is smaller than caffeine. The speed comparison is measured against a target that history says will move, and the people who reviewed the paper said so in the same breath as calling the work impressive. The 5-year forecast comes from a party with every reason to be optimistic, in a field where 5 years has been the standing answer for longer than 5 years. It is worth being precise about what the no does and does not cover, because the skeptical case and the promotional case tend to talk past each other by arguing about different things. What is not in dispute is that the experiment ran, that the measurements were taken, that the error correction result underneath it is real, and that the molecular structures agreed with an independent instrument. Those are facts, and nobody serious contests them. What is in dispute is how far any of it generalizes, how long the scaling takes, and what the classical comparison will look like once other people have had a few years to think about it. Almost every argument you will see about this result is actually an argument about the second list being presented as though it were settled like the first. If your question is whether the thing you have been promised has arrived, the answer is no, and anybody telling you otherwise is selling something. Now the yes. What was crossed in October 2025 was not a speed barrier. Speed barriers have been crossed before, and they moved, and they will move again. What was crossed, for the first time, was a trust barrier. For 6 years, this field produced results that could not be checked. Not results that were difficult to check, results whose outputs were structurally uncheckable, by anyone, by any route. The machines were performing feats nobody could confirm, in a language that did not permit confirmation, and the field knew it, and the field said so, and the most careful theorists in it named the problem out loud. And then somebody found a way to make a quantum computer produce the kind of output that science already knows how to argue about. A number, an expectation value, a quantity of exactly the same species as a temperature or a current. The sort of thing 2 laboratories can hold against each other. The sort of thing an entirely different instrument can be asked to confirm. And then, on 2 small molecules, in a laboratory at Berkeley, somebody actually did confirm it. That is what happened. Not a machine got faster. A machine started producing answers that can be checked, and then one of them was. Which is why I have been holding a phrase back all night. The echo is the measurement. I gave you that in the first few minutes, and it meant something narrow. A technical description of a protocol. Forward and perturb and reverse and listen. It means something wider now, because this machine was never really doing what we mean by computing. It does not grind through arithmetic. It is disturbed and reversed and listened to, and what comes back carries the shape of something you could not have asked about directly. That is not a description of a computer. That is a description of an instrument. And an instrument's job is not to calculate. It is to make something audible that was always there. Which is why the question in the title is the wrong shape, and why I think noticing that is worth more than the answer. Breakthroughs, as we imagine them, are events. A day, a moment, a before and an after. And instruments do not work like that. There was no night on which the telescope started working. Galileo saw 4 dots and did not know what they were. Astronomical spectroscopy, the thing that made telescopes into chemistry, arrived 2.5 centuries later. Van Leeuwenhoek looked at bacteria for years and had no idea he was looking at the cause of most human death. Germ theory took another 200 years to arrive and give the microscope something to look for. Nuclear magnetic resonance was discovered in 1946 as a curiosity about nuclei in magnetic fields, and put a scanner in most large hospitals on Earth, roughly 40 years later, for reasons nobody in 1946 had thought of. An instrument's first night is never its best night, and the person holding it is almost never the one who finds out what it was for. So when someone asks whether this is the breakthrough quantum computers have been waiting for, the honest answer is that quantum computers were never waiting for a breakthrough. They were waiting for the far less dramatic thing that every instrument in history has had to earn, one small, checkable result at a time, the right to be believed. And there is a version of this that is worth carrying beyond quantum computing, because you will meet the same structure again. Whenever a new capability arrives, the question the coverage asks is whether it works yet. That question feels rigorous, and it is almost always the wrong one, because it collapses a slow process into a pass or fail. The better question, the one that actually predicts what happens next, is whether the thing has started producing results that other people, using other methods, can check. Capability without checkability is a claim. Checkability is what turns a claim into a foundation somebody else can build on. Measured that way, the important sentence in the October announcement was never the one with 13,000 in it. It was the sentence that said the answer could be repeated. 2 molecules is not very much, but it is the inscription on the tower. It is the small, unglamorous, entirely checkable thing that has to come before anyone can reasonably take the machine seriously about the things that cannot be checked at all. And there is one more piece of this, which I have left until last because I do not think it resolves, and I do not want to pretend it does. We are building instruments whose answers no human being will ever be able to independently confirm. Every previous instrument had a chain of verification that terminated, somewhere, in a person looking at something with their own eyes. This one does not. Not because we have not built the right check yet, in principle, permanently. What we have instead is machines checking machines, tethered here and there, where we are lucky, to a physical experiment. And the very first genuinely useful thing one of these machines was asked to do was to measure how quickly information about a small disturbance becomes unrecoverable by anyone looking at only part of a system. Its first real job was to measure the rate at which nature hides things from us. I do not know what to make of that. I have turned it over a number of times, and I still do not know whether it is a coincidence or the most fitting fact in modern physics. But I know that it is the thing I keep returning to when I think about that chip, in that refrigerator, colder than anywhere in the natural universe, being disturbed once and then unwound, listening for a disagreement so faint it takes 1 trillion measurements to hear. Information that has spread out is not information that is gone. It is only somewhere we have not yet built the instrument to reach. There is a reason that particular phrase keeps coming back tonight, and it is not decoration. It has been true at every scale we looked at. It was true of Hahn's spins in 1950, fanned out into apparent noise and brought back by a single well-timed flip. It was true of the ink in the glass, present in every drop and locatable in none. It was true of the long-range structure inside those 2 molecules, encoded in correlations that no conventional analysis could untangle, and that a quantum machine could. And it is true, in the largest and least settled version of the idea, of whatever falls into a black hole, scrambled past any practical recovery, and, according to the mathematics that this very experiment measures, not destroyed. The same sentence, from a laboratory bench to the edge of a horizon. That is the kind of thing that happens in physics often enough that you stop being surprised by it and never quite stop being moved by it. Thank you for spending these hours with me, out at the strange edge where computing and the physics of information run into each other. If this is the kind of exploration you like to fall asleep to, a like or subscribe would mean a great deal. It is a small thing for you, and it genuinely helps me keep making these. And remember, the next time you hear that a machine has done something no human could check, that the interesting question was never how fast it was. Good night, and may you never quite hear the word breakthrough the same way again.